Hey, good morning, everybody. What we're going to do today is get started with a warm-up activity, go over some vocab, and then talk about the shuns, which is reflection, refraction, diffraction, and polarization. All right, so getting started on this warm-up. We're supposed to draw a harmonic series for an air column inside an open-ended pipe. Sounds like the pipe is open at both ends. So, question is, are we going to get a node or antinode? Remember that a node is where the standing wave is not moving, and an antinode is where you're getting the maximum change in air pressure or whatever it is for that kind of wave. So we're going to need antinodes at both ends. I'm going to switch over to dual wielding webcam mode. Kaplow. Alrighty. Pretty fancy, huh? That took a long time to configure, FYI. It turns out there's bandwidth limitations on USB hubs. Who knew? Okay. So I'm going to get to start out the harmonic series, I'm looking for the simplest possible shape that I could put in there that's a wave shape that meets those requirements. Now remember, center, antinodes would be far from the center as you can. I'm going to draw a wave like this. It was right in the middle. I've got antinodes. This is harmonic number 1. Okay, we're supposed to draw a series of these things. So let's do a couple. I'm going to redraw the pipe. We still need antinodes at both ends, but now I'm going to. So that's the one I want right there. And you guys know about number series. This is a series. Label the nodes and antinodes. Here we had 2 antinodes and 1 node. Here we have 3 antinodes and 2 nodes. And our next one, I'm expecting to see 4 antinodes and 3 nodes. Each of those is going up by 1 each time we do this. There we go. A little lumpy, sorry about that, but here's the third one. I marked the nose. Okay, that's the beginning of a harmonic series. You can keep going up farther and farther from there. Let's go on to the next question, though, which is if the pipe is 0.5 meters, and we know that the speed of sound is 343 meters per second in typical sea level air, good number to know. And what it's asking for is the wavelength and frequency for the first harmonic. So it's asking. And so one question is, how much of a wavelength is that in that pipe? So if it were a full wavelength, it would go to the middle, back down, back up to the middle, and back up to the top again. It would be completely starting over. The wavelength would end. We've only got half the pipe itself. Okay, so half is half a wavelength. How much is a full meter? I'm sorry, full wavelength. It would be a full meter. Like we know that the entire wave would end up over here, half a meter, and from here to here is 1 meter. This is a 1 meter wavelength. So my wavelength is. I'm going to get out my wave equation. I'm going to plug in some values. And after some amazing math, I'm going to find out that the frequency is 343 and the unit length. And that's a note that's a little bit below the A on a piano in the middle of the piano. That note is 440 hertz if you're a musician. Good one to know. Okay, so that was our warm-up. We graphed some height, making a resonance, and it being defined by the features of the space. In this case, they were open-ended. I put antinodes on both ends. If they were closed-ended, I might have a node there instead. We've made a harmonic series, which is step-by-step getting more and more complicated with a shorter and shorter wavelength. This one has 3 halves wavelengths in it, and so forth. Hopefully you guys notice there's a pattern there. I'll even write it like this. And so that's part of our harmonic series, and then we solve the wave equation to get some important info. So let's keep going now. Next up, I want you guys to pause the video here, go over your vocab, make sure you're cool with all this. We're going to be learning about the shuns today. Here's 3 of them. Here's the other one. And stop by office hours and let's talk about these vocab if you get a chance. That'd be awesome practice. Okay, so yeah, we're learning about these 4 vocab words. 3 of these involve changing direction, and the last one involves changing orientation. So you're going to identify something to do with direction changes in 3 different scenarios, be able to give examples of each, and then we're not doing Doppler today. Don't worry about that. So what these things are, diffraction is when a wave gets to a barrier, it can go around the barrier, or when it gets to an opening, it can not just go straight through the opening, but it can curve around the edges. That's diffraction. Refraction is when the medium changes, it causes the speed of the wave to change as well. Now you might be thinking this is limited to mechanical waves only, and you might be thinking that because mechanical waves have to have a medium, where electromagnetic waves don't. But the medium can actually affect electromagnetic waves too. So not necessarily. All waves can be affected by their medium. Light can be slowed down by some things. It doesn't ever go faster than the speed of light, but it can go slower than the speed of light. And then last up, reflection is also a sudden dramatic medium change, causing it to bounce off a surface. So you guys have definitely heard of this one. You probably already have a good intuition of how it works. We're going to do a little more focus on these other 2 here. And let's get started with some examples. So first up, can you hear, let's say there's a door in the back of the classroom's open. Can you hear down the hallway to the right and to the left of the door? And the doorway's open. Yes, you can. Can you see around the doorway to the right and left of the doorway? No, you can't. You can only see straight through the door, right? Like you can see what's directly behind it, but you can't see around corners. Well, so it seems like at first that sound is diffracting. Diffracting is when it bends around a barrier, but that the light isn't, because you can hear around the doorway, but you can't see around the doorway. Now, what's weird is it's because of the size of the doorway relative to the wavelengths of the type of waves involved. So light wave has a super, super, super tiny wavelength. Oh. Ooh, allergy season. Okay, sorry about that. So super tiny wavelength. And if you had a super, super tiny doorway, it actually would bend around. And there are these things which are on campus, which you guys don't get to play with since we're not in session. But basically, you can get light to bend around corners if the corners are small enough. So these diffraction gratings, they actually look like a clear piece of plastic, but they've got like 10,000 lines per inch etched into them. Too small for you to see, but they're the perfect sized doorway for the light waves, which have a very short wavelength to bend around. Whereas for the sound wave, it's actually about the same size as the doorway itself. And so it bends around corners of that size very well. Now here's a place where you guys might have noticed this. A really sunny day, you're underneath a tree, and the leaves have a really kind of sharp profile from the side, right? Like a leaf isn't very thick. And if the leaf is way above you, you may notice down on the ground that the shadows of the leaves are just a little bit fuzzy, like sometimes a double or triple image of a leaf kind of overlapped shadow. And that's actually diffraction happening. It is bending just enough around the leaf corner for you to notice that in the way the shadow shows up on the ground. So that's an example. Okay, now let's talk about some other stuff. Harbors. Whole point of a harbor, let's go to paper mode. Whole point of a harbor is to keep the ship from getting blasted by waves. So it keeps it safe, right? Yeah. Oh, this is a Viking ship. There we go. Okay. There we go. Viking boat. Okay. Got this harbor. And the waves, if I draw it like this, it's a diagram. If I draw it like this, it's a wavefront model. When they get to this barrier, what can happen? We're asking about diffraction. Diffraction is when a wave bends around a barrier or through an opening. What can happen is, if this wavelength, see the distance between 2 consecutive waves, that all matches the size of the barrier or the opening, then we will get diffraction. And what'll happen is, maybe not 100%, maybe not perfectly, but it'll end up bending around the barrier. And unfortunately, the waves, maybe not all of the wave, but at least some of the energy of the wave is going to get through and still blast the ship. So what could you do to try to mess this up? Better mismatch between the barrier and or opening size and the wavelength. You could Okay, another idea. And here are your ears. Okay, what's cool about this is, let's say there's a sound coming in from the left. I guess that's right for you. Oh, that's right for both of us. Okay, sound coming in from the right. It gets to this ear just fine. One thing that your brain is noticing is that it will also get to this ear with a very, very slight delay. The other thing it notices is, as to diffract around your head, and it gets into the other ear kind of filtered and not as loud, and with some different pitches involved. Sound, tell where it's coming from, using some aspects of diffraction as well as filtering and some other stuff, timing. There's a bunch of different signals to your brain that the sound is coming from over here, but diffraction is part of that. When you're setting up your speakers for your sound system, you've got the left speaker and the right speaker, and maybe you're running Dolby 7.1 and you've also got rear surround, left on right, and all that good stuff. Question is, does it matter where you put the subwoofer? Subwoofer is for really, really low frequencies, which is also long wavelengths, which are not at all the size of your ears or your head. They're much longer than that. And the answer is no, you can't localize it because it doesn't move around your head in the same way as the other more diffractable sounds. So you can basically put the subwoofer anywhere in the room and not notice that problem. There's also that annoying thing where you're stuck in traffic and the one car has got the rattling subwoofer. It sounds terrible. You're like, well, which car is it? And you can guess, but you can't be sure. Whereas you can hear the tweeters and the other speakers, the ones playing the higher frequencies because they have a shorter wavelength and it diffracts around your head better, you can localize it. So these are some real life examples of diffraction. Going along, diffraction bends around the barrier or through an opening. It works best when the wavelength and the dimensions of the object match up pretty closely. It works less well when there's a big mismatch. In fact, all right. Next up, reflection. Reflection's an easy one. So let's do a couple quick examples. Let's see. Switching back to this. So first up, we're going to flat mirror. Oh, first we're going to define it. Okay, if this is the reflecting surface, draw in a normal. Normal is a line that's perpendicular to the reflecting surface. Like, you guys remember the normal force? Which way did the normal force point? Perpendicular to the surface. This is a normal to the reflecting surface. Other one is the reflected ray. And what's very, very important is that this angle and this angle have to be the same. Okay, the incident angle and the reflection is probably already known. If I shoot a ball off the wall, right? How's it going to bounce? This way. If I shoot it straight up the wall, how's it going to bounce? Straight back. You guys already know this, right? Only thing I'm worried you might not know is that you measure the angle from the normal. You measure from the perpendicular line to the surface. You don't measure from the surface. Like, if somebody measured this angle, they would be wrong. Don't do that. Measure from the normal. Only thing I got to teach you there. Okay, let's do checking out your COVID-19 self with your sun pajamas on. I should probably get dressed. This happens at like 7 o'clock at night, right? Anyway, what we're going to do is we're going to ray trace, which is also something you may have heard of a graphics card doing for video gaming systems and stuff. Right at the mirror, what's the angle it makes? 0 degrees, which is to say straight back. If I aim a ray a little farther down, I draw in the normal. This angle and this angle have to be the same, so that normal goes there. And if I aim one farther down, draw in that, this and this have to be the same. Currently, you're looking at your foot there. Okay, so those are some rays that have traced that have reflected off the mirror following the law of reflection. What's cool is light in our brain goes straight. It's a virtual light ever behind makes it virtual. But we and there we go. Here's the image of yourself behind the mirror. Hopefully it's a good one, right? Okay, now you're like, virtual rays, it wasn't behind the mirror. What's going on with that? Not cool. Think about this. Ever seen a cat walk up to a mirror? They assume that there's another cat on the other side of the mirror getting ready to fight them. It's hilarious. Have you ever seen a baby? They assume they've just met another baby and this is a great time and the other baby's stoked to see him and they're making friends. Um, up until you're about 6 months old and start to realize what a mirror is and how it works. So these virtual rays, we do draw them in. The image does appear to be, so this is called the image. It's called the object for optics terms. We won't get too far into this, don't worry. There you go, that's reflection. Okay, so I really like. Rex. Okay, got the T-Rex. Here's the deep. Here's the driver. Here's a mirror. So driver looks at the mirror and sees that, looks in the mirror, sees that, and looks in the mirror and sees that. Oh, looks like they got a little bit of a blind spot here, right? Like, see all this? This is all blind spot. There's no angle you can get to the mirror and back from to see this zone right here. Gotta adjust your mirrors before you start driving away from T-Rexes, apparently. Anyway, I didn't do a good job driving my mirror. That's not the point. Point is that this is a hilarious scene in Jurassic Park because it says objects in mirror are closer. The mirror is A. And I call from the mirror the T-Rex. How far is the T-Rex from the driver? Hopefully you're taking minus A. Okay. And what's cool is though, you view this according to virtual rays, like this. And I'm going to make this distance also B, up to wherever the T-Rex shows up over here. I want to draw on the desk. Okay, so the image of the T-Rex is right here. How far does the T-Rex appear to be? Let's go this far, then go that much farther. Plus A. The T-Rex looks like it's this far, but it's actually this far. Hence, objects in mirror are closer than they appear. Which, if you don't think about, you can go like back up into somebody in a parking lot, right? A lot of you guys are new drivers. Please keep this in mind when backing up. Even a parking lot fender bender can be very expensive to repair damage. Last thing we're going to talk is this cool idea called a parabolic dish, of which we have a ton of examples in our classroom, which you guys will not get to see. Kind of stinks. We're going to go in at some point and like get all that gear and just do a massive demo day. Didn't happen this week. We'll try for next week. Okay. Anyway, um, let's say there is light for like miles away. At the time the light gets here, it's pretty much parallel, right? Like it's been going for so long that if it was going to spread out, it already would have. The remaining light is parallel. So I'm going to put a whole bunch of it's the next thing I'm going to draw the normals. And you can actually control all angles like that. And then what happens is the rays will reflect the equal angle on the opposite side of this. They all end up out of well done. All bounce back on the all the same like one. About a pair of it all concentrates. The light is focused to that spot. You can do things like have radio waves coming in from the satellite super far away that are very faint, and you can catch them all on a focus on the dish satellite TV. Or you can have this be a mirror, visible light, to focus this down to a dot, and then get that one dot really hot and like catch it on fire or something. There's a bunch of stuff you can do to focus down light using parabolic dishes. And the shape is a parabola. Although it turns out a circle and a parabola are almost the same for part of it. Like from here to here, it's close enough. You can also make a circular dish and get pretty close just using the part of it that's not like a parabola. And that's the cheaper way to manufacture these. All right, so reflection can do a couple things for us. Let's keep going. There we go. Dual wielding is tricky. Okay, all right, last up, refraction. This is a tricky one that we're changing the waves. So I think we talked about this already when we talked about S and P waves, but let's go for it again. What we're going to do is we're going to have an analogy to start out with. Got grass and quicksand. I've been in quicksand up to my waist a couple times. It's pretty fun. I think I told you guys. Did I tell you guys that story? Yeah. Okay. So, banks of the Rio Grande River in New Mexico found a patch of elephant mud, which is mud long enough to convert into quicksand. Then we spent time like jumping off, and we're having a great time. Don't cannonball though; it hardens on impact, kind of like the oobleck stuff, and it's jumping into quicksand. Fine. Cannonballing it basically rock hard. It really hurts. Okay. Anyway, we're playing along. Then this one guy, Robert, jumped in, and I remember us like all getting out, putting our packs on, and walking away. He's like, guys, don't leave me. Made sure, we made sure to come back about 5 minutes later, but gave him a good scare. We had that one coming. Running along, I ran the story pretty good in speed. They formed a wavefront, and they headed this in grass, so they were pretty here. They keep running. Oh, this person got stuck. He tried to go as far as the front. Now, you. Well, this person's stuck, and this person got stuck. This person gets harder, and these other ones are moving very slowly now. And what we've got is the wavefront is shifted. So when you get to a change in medium, medium means the substance the wave is traveling through, then it'll reorient the wavefront, but also a section heading. So anytime you guys need to think this through, figure out which side is the fast side, that is the slow side. I have 3 people. Can't go in. Who gets stuck? This one. Okay, turn for what? Refraction. Go that way. Okay, so basically figure out either who gets stuck first or who gets released first. And then figure out which way your 3 fingers have to bend because of that. Like, could be it is backwards. Okay, quicksands over here now. We're going this way. This person gets released first. This person is still going slow. I'm going to pivot it the other direction. All right, that's refraction. You can see this in a bunch of different examples. My favorite one is watching how waves break. Fun stuff. Okay, so here's an example of it in water. You guys have seen the thing where the straw looks bent. If you are trig ready, there's actually some very easy math for this. There's something called an index of refraction, which is the rating of active one. As in it goes full speed, the water slows it down by a factor of 1.33. But glass and oil slow it down even a little bit more. Okay, so the index of refraction is a rating of how much slower things go because of the material compared to the speed of light. And so what you can do is you can basically just plug in this math for I like to think of it as Snell's law. What is the index of refraction doing? It's slowing things down. Now, one thing you can do is get some situations where this math breaks, which is awesome. You can get it to where it can't possibly be equal. And then what happens is instead of refraction, you get and these things called fiber optic videos and stuff carry the data of the internet. And the way they're doing that is using such a high index of refraction that they keep the light bouncing back and forth to the very end. So fiber optic is something that uses internal reflection, which is like an extreme form of refraction where it's so far bent that it actually just bounces back in. It never actually moves to the second one. I'm not sure you guys will need to solve this. If you do, is that we use reflection in mirrors, and these are typically curved to be caved in. So this is called concave. Or bowed out, this is called convex. You can do the same thing with mirrors, and you can reorient the light, and you can create different focal points. And you might use this for glasses or contact lenses. You also use telescopes, microscopes, cameras, satellite dishes, all kinds of. So these are 4 different kinds of optics. We don't necessarily mean just the kind of light you can see either. Don't forget radio waves, microwaves, infrared, visible, gamma, X-ray, ultraviolet. I did that order, sorry. You should practice that order. So keep in mind all those other options too for what you can do with it. Here's a more zoomed in example. This is an example of which one? Convex lens. And we're tracking between the object and the image it produces, which is focused. And we're doing ray tracing. which a graphics card does at an extremely fast rate. That's the whole point of it these days. So they're tracing 3 rays, you can figure out exactly where the image is going to show up. This would be like where you put the film in the camera, for example, or where you put your eye if you want to see clearly and not a fuzzy image. Like this is all light from the top of the object. Over here, you want all that light to be put back together. Places that would be blurry. There's a bunch of stuff you can measure in distances too. We can do something hands-on with this, but I'd say don't worry about it for right now. Okay, last idea, polarization. This is where light is oriented. Basically, electric field and a magnetic field. And then like one photon can be like this, another one that they all reorient. And basically, when you put a polarizing filter in place, it cuts down the. What's cool about this is a lot of the times when things reflect off, they'll reorient to be all of the same orientation. So this is like a picture of mudflats. You're getting some glare. The glare happens to be polarized light. So in your sunglasses or in your camera, if you filter out light that got polarized when it reflected off the mud, you can filter out the reflected glare light from that while keeping the rest of the light, which is unpolarized. One other thing to note is of the light. One cuts out the vertical stuff, the other cuts out the horizontal stuff. Basically, nothing gets through unless you have a liquid crystal in between, which allows the light to reorient very slowly to make it through the second filter. So if you have an LCD display, liquid crystal light, which is pretty cool. In my class, you can. We talked about reflection. When light bounces off a surface, it follows the law of reflection, where the incident and we talked about refraction, which is where medium can slow things down, change the wave speed, and in the process, for light, there's a rating called the index of refraction, which is how many times slower it goes. So air and vacuum get 1, which is full speed. Other materials can slow light down. They'll get a number bigger than 1. That's how many times slower it is. And then we talked about diffraction, waves passing through or around a barrier can sometimes bend around that opening or around that barrier. They do so length, and the barrier doesn't work so well when they're super different. Last up, we talked about polarization, which is the idea that electromagnetic fields for light are oriented in usually random ways. Sometimes they'll get reoriented. You can make filters to cut that orientation out. That's about it. All right. I will get this up, and then but that'll do it. I'll see you guys around.